absence of any forces acting upon your body is known as weightlessness. Your body has literally entered a state of perpetual and stomach-churning freefall. Most humans can adapt to this nausea after a few unpleasant hours, but many biological functions of our body are hardwired for gravity thanks to billions of years of evolution here on the Earth. The muscles used for
Children, everyone has to understand, listen carefully. When you are going to the space, what is the nature of our muscle? There is an effect of gravitational force. How people can live. There is a change of muscle energy due to the low gravity. So these are all the factors all involved, influenced on human body, so that how it will be. So these points are explained here. Based on these points, we are going to create artificial gravity. So you listen and understand, write the important points.
Posture and skeletal support are no longer used and thus atrophy, losing up to 20% of their mass after a week. Astronauts on the International Space Station need to exercise for at least 2 hours every day to combat this muscle loss. But without gravity, our bones also wither, with astronauts losing 1% of their bone mass each month. Mostly to save money on special effects. The explanation for this is usually something like gravity plating, a wholly fictional technology. But how could we do this for real? The simplest way to create artificial gravity in the real world is just to accelerate in a straight line. If you were inside a spacecraft that was not just moving but accelerating at 1g, your inertia, which is to say your resistance to motion, causes you to be pushed against the back wall with the same force as that which the Earth pulls you down right now as you watch this video. In fact, Einstein postulated that the effect is so similar that there is no experiment you could possibly do on board that spacecraft to distinguish between being in a gravitational field versus just accelerating. In other words, inertial mass and gravitational mass are equal, something famously known as the equivalence principle in general relativity. This sounds promising, but accelerating at 1g for months, years, or decades would require engines with vastly greater sustainable thrust than any modern space vehicle. The N-Star Iron Thruster is probably the closest example we've ever built of such an engine. NASA's Dawn spacecraft, which visited Vesta and Ceres, used 3 Xenon iron thruster engines to sustain a record-breaking constant acceleration of just under 10 millionths of a g. It was an impressive technological feat, but it is a long way off providing useful artificial gravity. Is there any other way of generating artificial gravity then? The only other proven physics to do this is rotation. When a car turns a corner, you feel yourself pulled to the opposite side. That's the centrifugal force. Another example is a fighter pilot pulling a hard turn, causing a centrifugal force several times that of Earth's gravity. Acceleration, they are just the products of our inertia. They are not fundamental like electromagnetism, for example. Your body's matter will not change velocity unless acted upon by a force. And so if the aircraft around you moves to one side, you will not because of inertia. And so you find yourself slammed into the wall. But what if the wall wasn't a wall? What if it was the floor? Take a giant merry-go-round and spin it fast enough, and the occupants would feel pushed against the interior wall. If you did this in orbit where there are no other net forces acting, that centrifugal force to the wall would mimic gravity. You could stand on the wall, feeling the same downward force that Earthlings enjoy. The idea of a spinning habitat in space is arguably the most plausible way in which humanity might mimic gravity. It's an old idea too, toyed with in fictional tales such as Rendezvous with Rama, Babylon 5, Interstellar, and The Expanse. There are quite a few different concepts for achieving this with real-world physics, but today we'll focus on two foundational concepts that have been the most influential: the O'Neill cylinder and the Stanford torus.
90 AD. Can you imagine this level of detailing in 90?
Physicist Gerard O'Neill. In his 1976 book called The High Frontier: Human Colonies in Space, O'Neill laid out a strategy for the colonization of space through asteroid and lunar mining, which included the construction of a 5-mile diameter spinning cylinder with a length of up to 20 miles. The inner wall of the cylinder would serve as the floor for the inhabitants, providing up to 300 square miles of livable area. This is about the same land area as New York's 5 boroughs. O'Neill wasn't afraid to dream big, describing a habitat for millions of people with a total mass of several billion tons. Today it costs about $20,000 per kilo to launch into low Earth orbit, which means that the dry mass of the cylinder would cost about $100,000 trillion in launch costs alone. That's about 1,000 times the world's current GDP. A more realistic plan would be to build most of the habitat in space through lunar or asteroid mining facilities, which of course necessitates that those industries exist first. Even so, a space-based construct of this scale would be so expensive